All right, so let's get started. There's some administrative stuff to get out of the way first. First, if you hadn't seen the posts, online homework 3 is due today, so make sure that you do that. Unlike online homework 4 is out, we released it early. It's not due until after the midterm, but we figured some students might like to see the questions as part of helping study for the midterm. Homework 1, the written part, is being returned today. So one of the questions should already have been emailed to you. You should see it in your Andrew email. The other question should be done by tonight for some definition of tonight. Again, that'll show up in your email. The solutions for homework 2, are they out already or will they be out later today? They're out already, so the solutions to homework 2 are already out. So that should also be useful when you're studying. If you've been living under a rock, there is a midterm coming up. It is 2 days from now in class. 80 minutes, closed book, no electronic devices, closed notes except for one page both sides. Yeah, so good luck, getting ready for that. All right, so last time around, we were doing Newton's method, and we had described Newton's method for solving a system of nonlinear equations, right? And the Newton method was a way of finding the solution to those nonlinear equations by repeatedly linearizing the equations and finding the solution to the linearized version, right? Sounds familiar? Yeah? Everybody okay with Newton's method for equations? Okay, so what we'd like to do is use Newton's method for minimization, right, instead of for finding the solution to a set of equations. And it's really a pretty small change. Instead of finding the minimum of instead of finding the solution of a set of equations directly, if we start off with a minimization problem, right, if we want to minimize some function f of x, well then we can set the gradient of f of x to 0, right, and that'll find all of the local minima, maxima, and saddle points. And now we have a system of equations, right? The gradient is set to 0 as a system of equations, and so we can apply Newton's method to that system of equations, right? And I'm going to define g of x to be the same as the gradient of f of x, just to avoid some confusion when we're writing the equations. And so before we do that, right? So if our original function is from Rd to R, right? So we have to minimize, it has to be a scalar valued function, so the output has to be a real number. The input can be a d-dimensional vector. Then if that's true, then g of x, right, will be a function from Rd to Rd, right? The gradient is a d-dimensional vector. And so solving g of x equals 0, that's a system of d equations in d unknowns, right? So it should be exactly determined. And so what we want to do is, for Newton's method, right, what Newton's method does is it solves the system of equations g of x equals 0 by taking, we want g prime of x times the step direction delta x to be equal to minus g of x, right? That's Newton's method applied to g. And so what I'm going to do is I'll define the Hessian h to be the second derivative of f, which is the first derivative of g, right? Because g is already a derivative of f. And so then what we're going to do is solve h times delta x is equal to minus g, right? And that's the same, right? That's this equation here. And that's the same as Newton's method applied to the system of equations g of x equals 0. Okay? So it's got the same problems and the same benefits as Newton's method, right? It's expensive because we have to solve a system of equations here that's the same, it's a d by d matrix. So we have to solve a d by d system of equations. If we can do that quickly, for example, if the condition number of h is good, then Newton's method will very rapidly, meaning in a very few iterations, converge to a highly accurate solution, right? So the same problems and the same benefits. If we can't afford to solve a d by d system of equations, then we're just sunk. We can't use Newton's method at all. But if we can, it should take very few iterations to converge, all right? So let's just write out that algorithm in full detail, just to make sure that you have it on the slides. But what we're going to do here is we're going to add one thing, right? So we start with some point x1, and for each iteration, we'll compute the gradient and the Hessian of our function at that particular point. We'll solve for the Newton direction. That's this equation here. That's just copied from the last slide. And now, I'm going to add a little bit of a complication here. We're going to do something called backtracking line search, and I'll explain in a little bit what this does. But basically, the idea is that we're trying to wrap the Newton method in. We're trying to hedge our bets. We're trying to make sure that Newton's method doesn't go absolutely crazy, and in general, for an arbitrary function, Newton's method can take very large steps. And if it takes a very large step in the right direction, that's good. But if you're at a place where the Hessian is changing quickly, for example, then you might take a step in the wrong direction, and you don't want to take a very big step. And so what Newton's method is doing here, in particular what the backtracking line search is doing here, is it's making sure we don't take a very long step in a bad direction. Okay? And so the key thing here is that there's a step size, t, right? So we're going to add t times the Newton step to our current iterate. And there's a parameter beta, which is less than 1. And we start off with a step size of 1. And we repeatedly decrease that step size until some condition is satisfied. And the condition is basically saying that the step makes sense, that we get at least some decrease in our objective on that step. All right? And so the picture that makes this backtracking line search make even more sense is, OK, so we have our function f, and we have a direction d. And so if we go in that direction, that's a one-dimensional slice of the function f. And so it's going to look like this, right? It's going to be some smooth-looking function, right? And what we've done is we've Taylor approximated it here, right? And so it should keep, if it were linear, it would keep going down at a certain rate. And the amount of decrease that we would expect would be basically the gradient at that point times the length of the step, right? Now, because it's curving up here, right, we're not going to get quite that much decrease. And so what we're going to do is we're going to ask for at least half that much decrease, right? So we're going to look for a step, and of course half is an arbitrary constant. We're going to look for some constant fraction of that much decrease. And as long as we get at least half of the decrease that we expect from a Taylor approximation, then we're going to be happy. We're going to say it's a reasonable step. Otherwise, we're going to say that the step is too long. Now, is this going to terminate? Well, if the function is smooth, the Taylor approximation gets more and more accurate as you look on smaller and smaller scales. And so if you keep decreasing your step, eventually the Taylor approximation is going to become accurate. And eventually, you're going to get almost the whole decrease, right? And so a little bit before that, you'll get half of the decrease. And you'll take a step. So you will terminate as long as your function is smooth. Okay? So that's Newton's method with a backtracking line search. And yeah, so So this is a very nice, right? You can't do this backtracking line search for solving an arbitrary system of equations because there's no notion of descent there, right? But because we're doing optimization now, we can check our progress. And so now this version of Newton with line search, which is also called damped Newton or guarded Newton, this damped Newton algorithm will be much more reliable in general than Newton's method for solving a system of nonlinear equations, right? Yeah. So damped Newton has a couple of nice properties. Newton's method in general is affine invariant, meaning that if we have our original objective f, and we do a change of variables to the argument x, right? So we replace x by ax plus b for some affine transformation ax plus b, right? And then if we do Newton's method on f or on g, we'll get the equivalent sequence of iterates, right? Meaning that if we do Newton on g and we get a sequence of iterates x, and if we do Newton on f and get a sequence of iterates y, then if we start out at the same point, right, we start out with y1 equal to ax1 plus b, then in general we're going to get yk is equal to axk plus b, right? So that's nice. It means that no matter what affine transformation of your variable you take, Newton's method is doing the same thing. And in particular, if you started off with a bad affine transformation of your iterates, one that would make gradient descent go very slowly, right? Newton's method is going to say, you know, whatever, right? I'll just go quickly as if you had given me the right scaling of my variables, right? So that's a very powerful property of Newton's method. And I see a question over here? Yeah. Okay. So the other thing is that damped Newton is guaranteed to converge in the sense that if your objective function is bounded below, the objective value of your iterates, f of xk, converges. And if your function is, in addition, strictly convex, and therefore you have bounded level sets of your function, that means that the xk themselves also have to converge, right? So, and typically you get, just as for ordinary Newton, you get a quadratic convergence in the neighborhood of your optimum, which is very fast. It doubles the number of bits of accuracy you get with every step, right? So that's good, right? Damped Newton is a great algorithm if you can afford it, right? So that's, now I wanted to point out a comparison, right? So if we have a set of constraints, p of x equals 0 for some d-dimensional function p, we can directly apply Newton to p of x equals 0, or we can minimize, let's say, the norm squared of p of x with Newton's method, right? So we have two different ways to approach the same problem. We can either approach it as a system of equations or as a minimization problem. So I showed you one advantage of the minimization problem, which is that we can do guarded Newton if we have a minimization problem. But there's a disadvantage as well. And if you want to see what that disadvantage is, we can take a look at just solving a linear system of equations. So if we have ax equals b, and we solve that with Newton, right? Versus trying to, so we want to find that or minimize over x the norm squared of ax minus b. Right? So if you look at the Hessian of this, it will wind up being A transpose A is equal to, so this will be F, and that'll be grad squared of F. Right? And if you've looked at numerical linear algebra, A transpose A, the condition number of A transpose A is always the square of the condition number of A. So if the condition number of A is very small, the condition number of A transpose A is extremely small, right? And it could be small enough to give you round off errors. So basically, if your accuracy requirements are very high, it's a good idea to prefer the equations to the optimization. I'll put a, I'll say here that's only if the accuracy requirements are high. So that's if your accuracy requirements are high and if your original system of equations might be at all poorly conditioned, right? If you score a half, you get a quarter, right? That's still really good. But if you square 10 to the minus 10, you get 10 to the minus 20, and that could be a problem. Now, I give you this warning, but in machine learning, often we have very low accuracy requirements, and so it's not that big a deal. It's only a big deal, basically, if you run into numerical problems that prevent you from doing one of the steps of Newton's method. All right? So now let's look at Newton's method with constraints. Right? So one of the nice things about Newton's method is that it actually works quite well even if you have equality constraints in addition to an objective that you're trying to minimize. So what I've drawn here, this is just a sketch of an optimization problem with constraints. So our function f, that corresponds to the contours. And p here is this bright green line. Right? And so if we want to do an optimization problem subject to smooth equality constraints, well, first, before we do it numerically, let's take a look at this and see if we can get an intuition for what the solution looks like. So by looking at this graph, it should be possible to tell where the global or where the local optima are of this constrained minimization problem, right? So does anybody want to take a guess?
Almost at the peaks of those two.
Almost at the peaks. So you mean a peak here? This.
Oh yeah.
Right. So you. Right. Okay. So you move towards so right here. Yep, and then there'll be another local optimum over here, right? And what's special about those points? Like what geometrically, what could I say about the gradient at that point? So the gradient of f isn't going to be 0, right? The gradient of f is this line here at that point, and it's this line here at that point. What's that? That's perpendicular to the tangent of the constraint. That's right. And so another way of saying that is if you look at, so here, right, for the green line, right, there's just going to be, the gradient of p is going to be normal to the green line. And so what you're looking for is that the gradient of p and the gradient of f are parallel to each other. Right? And what that means geometrically is if you're thinking of f as a force that's pushing you, right? The gradient of f is a force that's pushing you towards things of better value, and then p is a constraint, right? You can't slide, you know, if it's tilted with respect to the constraint, you'd slide along it, but it's sort of pushing perpendicularly against the constraint, right? Meaning you can't move in any direction to increase your or decrease your objective value. Okay? So the local optima are the places where the gradient of f is equal to some multiple of the gradient of p. So that lets us do a Newton method then for optimization with respect to equality constraints. What that looks like is so I guess before we go there, let's do a little bit of notation, right? So we have here the gradient. And so if we have n variables and k constraints, right, then the gradient of f is going to be an n-dimensional vector, right? The Hessian of f is going to be an n by n matrix, right? It's the second derivative. And then here, this is the derivative, j here is the derivative of the constraint function with respect to the variables. And it's going to be a k by n matrix. It's called the Jacobian, right? And so if we, I'll just tell you what Newton does and then justify it, right? So in order to do Newton with constraints, we'll solve this set of equations, right? And that will give us our step direction x and some extra delta x, our step direction, and then some extra vector of variables lambda. Lambda is called a Lagrange multiplier. And if you work it out, this first line is the generalization of the gradient of f is equal to some multiple of the gradient of p, right? And this line here is just the linearized version of p of x equals 0. So I'm not going to derive it, but if you do go and put in the Taylor expansions in the appropriate places, you'll get that the second block of equations winds up trying to satisfy your constraint for you by setting a linearized version of your constraint to 0. And the first block of equations tries to make it so that your gradient of your objective is parallel to the gradient of your constraint. So, so Newton's method is great in this sense, right? It lets you handle, it's the first method we've looked at that can handle constrained optimization, right? And in fact, turns out that you can handle inequality constraints as well. So suppose that we want to minimize some function f subject to p of x bigger than or equal to 0, rather than just p of x equals 0, right? Now, this is not a smooth optimization problem, meaning you can't apply the regular Newton method. The reason it's not smooth is that you discontinuously jump from feasible to infeasible when you cross the barrier, right? When you cross the constraint. So what people sometimes do is called the barrier method. So if you look at the graph here, right, the graph of negative log x. So if we take negative log of one of the components of p, right? That's going to be, it'll be infinite on one side of p. By convention, the log of a negative number is infinite. And on the other side of p, it'll be something finite, right? And it will be something really big as you get close to the constraint, and it'll be something smaller as you get farther away from the constraint. And if you scale, right, if you take let's say, so this here, right, this is log x, right? And if you take log x over 2, right, it flattens out a bit. Log x over 10 flattens out a bit more. And you can see that minus log x over 10 already pretty much looks like the indicator function of the constraint, right? It's, it's basically 0, pretty close to 0 as you're positive. And then all of a sudden, when you get close, it shoots up to plus infinity. Right? And so if you're minimizing a function that looks like this, right, you're going to wind up getting pushed away from the boundary. Right? And the higher the multiple of log, the more you're going to be pushed away from the boundary. The smaller the multiple of log, the closer you're going to be able to get to the boundary before the penalty starts kicking in. All right? So, so what people do is they'll try and solve this problem for a bunch of different values of the multiplier t, right? So 1 over t here is the multiplier on the log term. And so if you make t be small, let's say 1, right, you're going to be pushed away from the boundary a lot. It'll be a very smooth problem, but you will not have a very accurate solution because the barrier function is pushing you away from the boundary. On the other hand, if you make t be really big, 10 to the 20 or something, right, then you're going to be able to get really close to the barrier before the penalty kicks in. but it's not going to be as smooth a problem, right? It's going to look, very close to the indicator function of the constraint, which has derivative discontinuity at 0. So what do people do? They start with a small t and initialize to some feasible point, and they'll find the optimum for that t using damped Newton, guarded Newton, right? And that's going to work pretty well because it's a relatively smooth problem because the multiplier on the barrier term is small. Then they save that point, and they change the barrier, and they use the old point to initialize Newton's method for finding the minimum of the updated function, right? And so what do I mean by change the barrier, right? We take some constant beta bigger than 1, and we multiply t by beta so that t gets bigger, right? And therefore, the multiplier on the barrier gets smaller. And because we initialized with, so if you don't change beta very much, if you don't change t very much, if beta is close to 1, then the optimum isn't going to move very far. And so if you warm start with the result of the previous optimization, you're going to be really close. And so it won't take very long to solve the new problem, right? And so you have a trade-off. If you change the barrier parameter t, if you change it slowly, you'll be able to find the optimum on each time through. You'll be able to find it very quickly, but it'll take a lot of updates of the barrier parameter, right? And so this seems like a horrible hack. At least it did to me when I first saw it. But believe it or not, it turns out that you can, by carefully choosing the rate at which you which you change the barrier parameter, you can often make polynomial time algorithms. As a matter of fact, sometimes these are the state-of-the-art algorithms. They're the absolute fastest algorithms that anybody knows for solving certain types of constrained optimization. Yes?
Could you go back to the previous slide? So, sorry, could you explain again why the first problem is not smooth?
Right. So Newton's method, right? It assumes that you're trying to find the optimum of a smooth function, right? Yes. And the only way to represent a constrained optimization using Newton is to say, well, the objective is infinite outside the constraint set, right? And so there's a very big discontinuity from something finite to something infinite as soon as you try and cross the boundary of the constraint set.
I see. Yeah, and the second thing is, maybe should the plus be a minus sign?
Yeah, it's minus log, right?
On the left equation.
Oh, yes. The plus here should definitely be a minus sign. Thank you for finding that. Yes, so that wouldn't work very well at all if you had a plus sign there. All right, so any more questions about this idea of a barrier method? All right, so that's good. So in particular, for solving moderate-sized quadratic programs, this leads to what are called interior point methods for convex programs. And for solving like medium dimensionality quadratic programs to very high accuracy, these interior point methods are the best class of methods that we know of. All right. So this is what a barrier method looks like. So what I've done here is for different values of the barrier parameter, I've plotted the solution to the optimization problem, right? And it lies along a smooth curve, which gets to, as you push the barrier parameter up to infinity, it gets to the optimum of the original constrained optimization problem. So here the optimization problem was to optimize a linear objective, this function here, within the clear set, right? Without violating any of the blue constraints. Whereas if you let the barrier parameter go towards 0 in the other direction, you get very far away from any of the constraints, but you have a very smooth optimization problem. And just numerically, Newton's method took 16 or fewer iterations for any t between 10 to the 6 and 10 to the minus 6, which is what's plotted here. And so Newton's method turns out to be very good for solving problems of this form. And that's without the warm start. It takes even fewer iterations with a warm start for finding each one of these points. And so you can see when t is 0, you pay attention essentially only to the constraints. And when t is infinity, you pay attention essentially only to the objective. And in between, you're trading off between the two of them. And this smooth path, by the way, is called the central path, or the path of analytic centers. But central path is shorter. All right. So, so that's all for Newton's method. Any last questions before we leave Newton's method? So now I want to go to the opposite extreme. So you guys have seen gradient descent and also stochastic gradient algorithm in the homeworks, right? So the stochastic gradient method is when you take your weight vector w and you update it by moving a step along the negative gradient, but instead of having the exact gradient, you have, instead of having the exact gradient, you just have something whose expected value is the gradient and which has bounded variance, right? So this is in many senses the exact opposite of Newton's method. It scales very well to high dimensions, right? It doesn't require you to invert any big matrices, but the convergence rate is absolutely horrible compared to Newton's method, right? So when I say that the convergence rate is absolutely horrible, I really mean it, right? So if we want the typical convergence rate is something like the accuracy epsilon is going to be order of 1 over the square root of the number of iterations that you take, right? So if you want accuracy 10 to the minus 10, you're going to have 10 to the 20 iterations, right? Not even Google's cluster can do that. So if you want accuracy 10 to the minus 10, stochastic gradient is basically out. There's just no way you can use it for that. And that's that's for a well-conditioned problem, right? And if you have a multiplier of the condition number in there as well. And so if you have something whose condition number is bad and you want accuracy 10 to the minus 10, you're even deeper in than you were before, okay? On the other hand, in machine learning, often we don't care about getting accuracy 10 to the minus 10. What we do care about is the fact that somebody dumped like a truckload full of hard drives of data on us, and we want to find a pretty good solution, meaning pretty low objective value, even in the face of this huge pile of data, right? And it's in this sort of case that stochastic gradient really shines, because basically what winds up happening is that every iteration of stochastic gradient is really, really cheap, right? So in Newton's method, we have to calculate the gradient and the Hessian exactly and then solve a system of linear equations, right? In stochastic gradient, all we have to do is evaluate the gradient, and we don't even have to do that very well, right? We get something whose expected value is right, and its variance is anything bounded, and stochastic gradient will still work. Right? And so often it's much, much faster to get an unbiased estimate of the gradient than it is to do an exact evaluation. A good example of the sort of situation where that's true, so if you remember the typical machine learning optimization problem was something like L of W is equal to F0 of W plus sum over I of Fi of W. Right, and let's say I equals 1 to n. Right, so F0 was something like our log prior, and Fi was the log conditional likelihood of the ith training example. So if we want an unbiased estimate of the gradient, we could take, for example, g to be equal to the gradient of F0 at W plus let's take actually n times that gradient plus the gradient of fi of w, where I, the index here, is chosen uniformly at random on the range from 1 to n. Right? And so if you look at this, right, we have a 1 over n probability. Sorry, I got the n in the wrong place here. That should be that and n there. So, okay, I have a 1 over n probability of choosing each one of the fi's, right? And then I multiply that one by n. So the n and the 1 over n cancel out. And my expected value is, in fact, just the sum of all of the gradients of the fi's, which is the correct final gradient, right? And so here, if there's a billion terms here, I evaluated 2 of them, right? And so that's, you know, a billion over 2 times cheaper, right? So every iteration of stochastic gradient can be almost free compared to iterations of more complicated methods. It's just that you need an awful lot of the iterations of stochastic gradient, right? Oh, and the reason, by the way, so I separated out, I treated the gradient of f0, I treated that separately. That's because often in a problem like this, the regularizer, the gradient of the regularizer has a larger norm than the gradient of any of the examples. And so I could have just randomly selected from 0 to n instead of 1 to n, but then I would have gotten a larger variance in my gradient estimates. So a cheap way to get rid of, to lower the variance of your gradient estimates is to pick out your regularizer, always include that, and then randomize over, over the remaining terms. Right? So, let's see. So a good example of the type of problem that you might want to use stochastic gradient for would be very large-scale regression or classification, right? So you would get the aforementioned truck of hard drives full of training examples, and you would want to solve for the parameter vector, right? And in fact, a lot of machine learning that's deployed out in the real world is done exactly this way. You get, you know, a web crawl's worth of data. If you happen to be some very large information technology company whose name begins with G, and you get a very large cluster, right, of computers, you store all of your data on your computers, and you run stochastic gradient or some elaboration of that, right? And it's basically, in some cases, the only way to scale. All right, so that's stochastic gradient. I only want to give one more example of or I guess one pair of examples of additional algorithms. And this is one that you may not have heard of, but it's a pretty useful one. So mirror descent and stochastic mirror descent, they're similar in many ways to gradient descent and stochastic gradient descent. The difference is that they let you take advantage of some kinds of structure in your problem. So let me define plane mirror descent first and then stochastic mirror descent. So what we do is we pick something p of w, which I'm going to call a penalty function. And p of w, it's typically going to be convex, not necessarily smooth. And it's going to let you encode some information about your problem. And I'll talk about that in a sec, how it lets you encode. And what you do is you do a 2-variable loop, right? So just like gradient descent, you keep a variable w, which is the thing you're trying to optimize. But in addition to that, you keep a new variable z, which is interpreted as the average descent direction so far. Okay? And what you do then is you update z with the gradient, right? The same way that you would have updated w with the gradient in gradient descent. But then to get w, you solve a small minimization problem, right? And we, in order to run mirror descent, we have to be able to do this efficiently. Or I guess it doesn't have to be efficient, but you're going to be very sad running mirror descent if it isn't efficient. Right? So P, in addition to being convex, it has to be something where we can solve problems of this form moderately quickly. Okay? And then, so G here is going to be your gradient if you're doing exact mirror descent, or it's going to be something whose expectation is your gradient if you're doing stochastic mirror descent. Right? So it's a small elaboration on gradient descent. We're keeping two iterates, W and Z, instead of just W, and they're connected by minimizing this penalty function P. And to make an even stronger connection, what if, so if we say P is equal to W transpose W over 2, right? Then the gradient of P is equal to W, right? And so then this minimization problem here, right? The solution we get by setting the gradient to 0. So we set gradient of P is of W is equal to Z, right? Which is the negative of the gradient of that second term, right? And so we get W equals Z, right? And so if we choose the penalty function, which is the squared norm of W over 2, then mirror descent reduces to gradient descent, right? You're just keeping track of W, and you're adding your gradient to W. But more generally, if you choose a different penalty function, you're going to get a slightly different optimization, right? And you'll be able to solve some problems faster by picking P appropriately.
Can you give some intuition on what P is?
Yes. So that was actually going to be the next thing that I said. So if you have something of the form minimize f0 of W plus sum of fi of W, often what people will do will be to choose that P is equal to f0, right? So you'll pull off one of the terms of your optimization. And this can work well if, for example, f0 is not smooth, whereas all of the other terms in your optimization are smooth, right? Because the convergence of gradient descent depends on the smoothness of the functions. And so what mirror descent can do is it can let you pull off a non-smooth term so that you can get convergence that depends only on the smoothness of the remaining terms, right? Another thing that you might do is if you know something about the geometry of the problem, for example, if you know that, your vector W represents a probability, right? So then your probability has to be constrained to be inside the simplex. And that's a pain to deal with a gradient descent algorithm. So what people might do then instead is make the P be the entropy of W. And the entropy, or the negative entropy of W, right? And so the entropy of W, negative entropy of W, is curved up strongly at the borders of the simplex. And so it's going to be like a barrier method. It'll push your iterates away from the borders of the simplex and turn it again into a smooth optimization problem. All right? So that's a couple of examples of how you might choose this penalty function. So does the structure, the form of the algorithm make sense to people? All right. So yeah.
Can you elaborate, like, why are we doing P minus Z transpose W? Like, where does that come from?
I mean, I guess one of the best intuitions for that is, let's see. So I guess first, one intuition for that is if you choose P to be squared norm of W, right, then you duplicate gradient descent. And so this class at least contains one reasonable element. No guarantee that any other elements are reasonable. The other thing is that, okay, if we are so let's see. If you look at Z transpose W, right? So that's the sum of the gradients, or or let's look at minus z transpose w. That's the sum of the gradients dotted with w, right? So if your average gradient gradient direction is pointing that way, right? That means that on average, all of your loss functions have been increasing that way, right? And so you would like your weight vector to be that way, right? You want to have it in a direction where all of your loss functions have been decreasing so far. And that's exactly what the minimization does. Subject, right, it uses this penalty function p to keep you from going to minus infinity, or going infinitely far in that direction. But subject to that, it tries to move your weight vector in a direction where your previous loss functions have been sloping downward. Does that make sense? Yes.
My question is actually, will this also kind of introduce some kind of bias? Like, if it happens that previously there are many erroneous gradients that pointing to the wrong direction, then
right.
it will further encourage.
Right, right. So the question was, what if there were a lot of gradients where you took them at the wrong spot in the function and they're pointing in the wrong direction? That's actually a problem with gradient descent as well, right? So if you, at the beginning of gradient descent, start off in some region of the function where the gradient is pointing you away from the optimum, then you're going to be, you're going to move away from the optimum, and that's going to be carried through to all future iterations of your gradient descent, right? What you're going to have to do then is, once you get into the right region where your gradients are pointing in the right direction, you're going to have to get a bunch more of them to move you to the optimum than you would have if you had started in the right region, right? And that's true for mirror descent as well. If you start in the wrong region and your initial gradients are misleading, then you get misled. Right? And you have to then get more information from the right region of the function in order to succeed. Yeah?
How is the efficiency for the convergence?
Right. So that would be the next slide. So the efficiency is basically very much like gradient descent, except that if you can correctly encode some geometry of the problem in this penalty function p, you're going to wind up getting the conditioning of gradient descent to be better. So basically, it's like gradient descent, except that you might be able to get a better one of the gradient descent convergence rates than if you had just used gradient descent on the raw problem. Right? So if you remember, gradient descent had all of these different convergence rates ranging from 1 over the square root of t to e to the minus t, right? Depending on properties of the function. And so if you can pull off some annoying part of the function into p, you can make the rest of the function smoother and get one of the higher convergence rates. Right? So basically, you should choose mirror descent or stochastic mirror descent when you can efficiently evaluate either the gradient or something whose expected value is the gradient. The accuracy requirements have to be not so high, right? So for any stochastic algorithm, the best you're going to do is still not very fast. So you can't have a very high accuracy requirement. And you need to be able to encode something useful about the problem in the choice of penalty function. For example, the conditioning of the problem should be OK after you pull out the penalty function. All right. So I think that was all I wanted to say about that. Shall we swap to the next topic? Okay. Oh, there's a question. Yeah, while we're swapping, there's a question.
So here in the mirror descent, we choose 2 variant, then we choose 4 variant, and that will include this calculus.
We choose.
So here we just choose the variant for the loop. For example,
There's a 2 variable loop, right? Are there algorithms that have 3 variable loops or 4 variable loops that go even faster?
Right.
Yeah, I think there are. There's a bunch of algorithms due to Nesterov that have varying numbers of variables in the loop. Conjugate gradient is another 2 variable loop, and LBFGS, limited memory Broyden-Fletcher Goldfarb Shano, which is you're not going to be tested on that name, but you can look it up. And MATLAB actually has, I think, an implementation of that, and that keeps actually a tunable number of iterates. Right. The basic idea with keeping more iterates is to be able to choose your directions more wisely. Sometimes they do it by remembering directions that you've previously chosen and choosing something that doesn't undo what you've done in those directions before. And other times the intuition is more like this, that you're trying to get rid of some unpleasant part of your algorithm, of your objective function. Yeah. All right, more questions? All right. There you go.
Okay, I presume the other one is not working? Oh.
Yeah, I couldn't get the other one to work.
Okay.
I don't know why.
Yeah, it's showing up on the screen, but not there. All right, that's okay. All right, so let's start with another topic, which of course we won't finish today, but we have about half an hour, so it's, we can get through at least some of it. And this is sort of in a different flavor than the methods we have talked about before, though of course we'll see how you can think of some of them as being non-parametric. So we'll talk about non-parametric methods, and I'll define what that means. And in particular, we'll be looking at this for both. So far we have done classification and regression. We haven't talked about density estimation as much. But I would like to start off with density estimation because that goes nicely into classification or the non-parametric classification well. Okay, so we'll talk about all of these techniques, but more in a non-parametric framework. Okay, so let's start by what we mean by that. So far what we have seen are actually parametric methods. What that means is that we assume some kind of a functional form for the involved distributions. Okay, so we have assumed things to be Gaussian, to be Bernoulli, like the probability of a prior probability of a class, or the class conditional density. We have assumed it to be Gaussian. Multinomials, even the logistic function, right? When we defined that form, it had a few parameters, which were the weights of the features, and you defined what the p of y given x looks like as a function of those weights, right? So again, we assumed a form that had a bunch of parameters in it, right? So, and even when we do regression and we talk about linear and quadratic fits, or polynomial fits more generally, we still have parameters, right? Which are the weights of the different features, possibly the nonlinear features. And you can think of those as parameters in your problem, right? These functional forms could have been for either p of x given y, which is the class conditional densities, the class priors, or directly on the probability of the label given the feature, which would, like in logistic regression, right? And in all of these problems, you're estimating parameters of a Gaussian, like the mean and the variance, probability of a coin flip, right? That was like in the class prior, we had the Bernoulli parameter, or some set of weights, like in linear regression or linear classification, logistic regression, all of those, right? We also talked about, I guess, beta, which was regularized versions of when we were doing this least squares laws, but with some penalty, right? All of those things. So what are the advantages of such methods? They have few parameters, right? And so the number of data points you need to learn typically scale with the number of parameters, and that tends to be not too large, right, once you have a fixed number of parameters. What we'll talk about today is methods that either don't have parameters, or actually they have parameters, but the number of parameters can actually scale with the number of data points. That's what really makes them non-parametric. So even though they are called non-parametric, one good way to think of it is they do have parameters, but they are not fixed. Fixed as in they can change. How many parameters there are can change as the number of data points increases. Okay. So why would you want to do that? If you have more data points, you can hope to fit better or more complicated functions, right? Sort of intuitively makes sense that you should be able to, if you have more data points and your underlying ground truth is more complicated, then you should be able to employ a more complex model. Whereas even if your underlying function was very complicated and you're trying to approximate it given only few data points, then maybe you should use a simpler fit, right, to avoid the risk of overfitting. So that's what non-parametric methods get at, but and that's exactly what the sort of downside of parametric methods is, that here you're making strong distributional assumptions, so you're often limited to simplistic modeling of your data, right? So non-parametric methods allow you to fit more complex functions as you get more data points, right? And why would you want to do that? Well, there are several examples. Here's just one I pulled where these are handwritten digits. So these are images of handwritten digits. Every single point here is actually a 7 or a 1 or a 3 written by hand. And what I've done is just projected that into by simply doing into a 2D space. We haven't talked about PCA, but this is just looking at principal component analysis on the set of all handwritten digits in a particular database. So we'll talk about how to get those features, but right now you can think of every point as representing one handwritten image. And you can see for some of them, maybe it makes sense to do, say for every digit, we want to fit a model. So some of them, maybe it's reasonable to say, well, for the ones, maybe you can fit a Gaussian here, a narrow, right, a Gaussian with a narrow covariance matrix. For 2, maybe it makes sense to fit a Gaussian, maybe some of these 3, 8s, and 5s. But look at the shape of these guys, 4, 7s, and 9s. It's clearly not, I mean, there's no natural parametric model that comes to mind which can fit something like this, right? This is like sort of arranged in an arc, higher density here, sort of lower density as you go towards here. So just to give you a sense there are lots of data sets where the simple models that you have in mind may not be a good fit, and you might want to do something more complicated, right? Okay, so that's where we'll go to non-parametric methods. They don't make any distributional assumptions in the sense they don't assume a particular form for the underlying distributions. And as I said before, as we have more data, we will be able to learn more complex models. Or another way to think of it is we let the number of parameters sort of scale with the number of data points, which we haven't done so far. And we'll be talking about this in the context of all of these problems. So let's start with density estimation. All right. So what's the goal of density estimation? You're given a bunch of points, right, samples, and you want to be able to figure out what's the underlying density, right? So it's just about learning a distribution. And one non-parametric method that can do that is histogram density estimate, right? So what's the goal? Once again, what's the goal of density estimation? You're just given a bunch of points, right? And I haven't set up. Let me just move the screen out. Oh, sorry, wrong one. Move the screen up. And yeah, before I talk about this, I just want to make sure that everybody understands what density estimation is, right? So suppose we have, let me finish this. Okay, suppose we have only a single feature, right? And then we are given some data points. Then I can sort of plot those data points here, right? So for example, this is the scores of people on the first students in this class in the first homework. And we can draw what their scores might look like. Maybe few people who got really high, few got low, and maybe there were some in the tail, something like this. And you want to estimate what the distribution is, then all I'm saying, this may or may not be a good representation. I actually have not looked at the distribution yet. You might think, well, maybe the underlying distribution kind of looks something like this. I don't know. Right? So just trying to find this distribution given these samples is what density estimation is all about. All right, so I hope everybody's on the same page now. And of course, this was done only for one feature. You could be doing this for data points that are characterized by many features. Right? Okay, so the simplest non-parametric method to do this, and really this is what you would intuitively do if you had to estimate what this underlying distribution looks like, is you would bin up your data and just count how many points, because what you're essentially doing is you're estimating what's the probability that a point falls, takes a particular value, right? Or so you're just essentially one estimate is you're just counting how many points fall in a bin, divide by the total number of bins. That's your estimate, total number of points. That's your estimate of how frequently can you expect a point to lie in a bin, right? So that's, you're just estimating the underlying distribution, right? So all we are doing in histogram density estimation is we take our feature space, we divide it into bins of equal width. Here delta will be denoted as the bin width, right? So number of bins is just 1 over delta, right? That's how many bins you're choosing. And we're just going to estimate the underlying, if we had to estimate the underlying distribution, the probability distribution, then we would just be saying how many points fall in that bin divided by the total number of points, just the relative frequency, right? And if you're interested in probability density, not the distribution, then we also divide by the volume of that bin, right? Because density is just the derivative of the probability distribution. So we divide by the volume, and here I've written delta I to indicate you could possibly have a different bin width for each bin, but usually it's taken to be the same. In fact, in histograms you take them to be the same. All right? So that's just an estimate of what your probability density looks like. And you do this for every bin, and you get a non-parametric histogram density estimate. Of course, the key quantity here is this bin width, right? That's like a parameter. So why are we calling it non-parametric? Because we'll allow this bin width to possibly change as depending on how many data points we have. Okay, so really that's what makes it non-parametric. And you can already see what the effect of changing this bin width is. So if we use a very small bin width, then that's shown here. So these bars are just the counts of how many points might fall in each bin, right? And this was actually the underlying density, the green curve, from which points were sampled. And you can see that as I increase, so this is the same set of points. All you're changing between these different figures is the bin width, right? So as I change the bin width, make it larger and larger, you can see that this is the underlying density, and this is essentially my approximation to it, right? It's just the fraction of that, how many points fall in a bin, divided by total number of points and the bin width. So you can see that that's what's happening to the approximation. It's becoming poorer and poorer, right? I sort of have maybe a better, maybe over here it seems like it's doing a good approximation of this underlying density, but here it's getting too coarse, and maybe here also it's, okay, what's happening here is that it's actually becoming, there are not enough points in each bin, right? So what you want is in some sense a trade-off where you don't take these bins to be too large, otherwise you're not doing a good approximation of your function, underlying function, and you don't want them to be too small so that not enough data points fall in each bin, right? So that's really the trade-off in terms of choosing the number of bins, and we can see that this delta bin width actually acts as a smoother, right? And as we go on increasing it. All right, so what's really happening? Understand more the effect of this bin width. Let's look at what our density estimate is, right? That's just, as I said before, it's just the fraction of points that fall in each bin divided by the size of that bin. That's the density estimate. Another way to write it is just like this, right? I'm just counting. I replaced ni, which was the number of points in bin I, by an indicator function which says if a training point falls in that particular bin or not, right? And the reason I did that is so we can understand the effect of this bin width by evaluating the bias of this estimator. Okay? So if you remember, before we had talked about the bias is essentially about how the mean of your estimate, how close that is to the underlying ground truth, right? That's how we had defined bias when we were talking about regression. So that is the bias here. It's just the expected value or the average value of your density estimate. And if you look at the expected value of this function, what's that? So we have the 1 over delta. We are taking the expected value is over the training points, right? So if I move the expectation inside, I get expectation of this indicator function, right? And what's that? It's just the probability that the point falls in that bin, right? Hopefully people are okay with that. So all we get is that, and of course you get n times that probability, right? That probability is the same for all data points because they're IID. So we just get 1 over delta times the probability that a randomly drawn point falls in that bin, right? So when is this? We are talking about this is what our mean predictor looks like. And bias is how far it is from the true underlying density, right? So if the true underlying density was P, right, I can write the probability that a point falls in that bin as just the integral of that density over that bin, right? Density is just the derivative of the probability, or probability is integral of the density, right? So that's all I've done here. So what we are asking is, when is this thing a good approximation of the density at x, p of x? So when do people think that happens? So delta controls somehow how good of an approximation you'll get, right? So should delta be large or small for this to be a good approximation of p of x? Think of what this is doing. You have some underlying function, right? And you're trying to estimate it at x. And what this is doing is it's taking all points that lie in a bin around x, and it's just averaging that function over that bin, right? So if we want that average to be close to the value at x, what should delta be? Small, right? So if delta is small, then we expect that this integral, right, will be actually, it will be as if we are taking p of x, the value at x, and just multiplying it with delta, right? It's as if that the width is so small such that the density is effectively constant in that bin. It's close to p of x. So if delta is that small, then you expect, right, as we do here, that you get the average value is actually equal to p of x for very, very small delta, right? So another way to say it is our estimator p hat of x is unbiased, which means its mean is equal to the true value if delta is very small, or it's more and more biased the larger we make delta. All right? Okay, so that's really where we arrive at sort of, again, this notion of bias variance trade-off now for density estimation. We can write how far our estimator is from the true underlying density that generated the data points by looking at how far is the mean of that estimator from the true density, which is the bias, and we just saw how that bias is controlled by the bin width. The smaller you make the bin width, the better the bias is. And the other part is how much does it vary from its mean? How much does the predictor p hat of x vary from its mean? And that's the variance as we had before, right? That if I take a new draw a set of new n training points, then how much will my estimate change? And you can imagine why that happens, right? Like if my underlying estimator was just the fraction of points that fall in a bin, right? So if you can already see the effect of the bin width. When will my variance be high? What should my bin width be for the variance to be high? Variance means if I draw another sample, I get a very different answer, right? It's unstable or varies a lot. Yes, it will be small. Why? We just discussed it, right? So why, if we have very small bin width, we expect our estimator to vary a lot? Not enough points, right? So suppose one bin had only 1 point earlier. If I take another sample, most likely I'll not get any points there, right? So the number of points per bin can actually vary quite a lot if my bins are very small. Whereas if the bins are large, then the number of points that come from that bin will be more stable. So intuitively also it makes sense that the smaller the bin width, the worse the variance. Or to get a better variance, you require a larger bin width, right? And that's where again, you can see how setting this bin width controls this bias variance trade-off, right? So as we talked about before, the choice of bin width affects the bias. The bias is good if the bin width is small, right? But if you look at when is it more stable, so that the mean value and any particular prediction on a specific training data set looks good, that is when your bin width is large, then your estimator is more stable, right? So you get smaller variance if the bin width is larger, but you get worse bias, right? So really that's what implies. A smaller delta implies you have a lot of bins, so you have smaller bias but larger variance, and vice versa. Are people okay with this? We just discussed? Right. Okay, so we can see that here. Once again, the same figure we had earlier, the choice of the number of bins. And you can see that if we plot the overall, actually I shouldn't have written mean square error here. This is actually just looking at p hat x minus px in absolute value. But we just saw it before. We can think of that as decomposed into a bias and a variance term, right? So you again see that the overall curve does this as we increase the number of bins, right? So again, there's a trade-off going on here that as we increase the number of bins, our bias is getting smaller, but the variance is getting larger, and so the overall curve still does this sort of roughly U-shaped curve that we had talked about earlier with bias and variance trade-off, right? Bias goes down, variance increases. Earlier we had studied it as a function of the complexity of the model, so here the complexity is actually controlled by how many bins you have or what's the bin width, right? That's controlling the complexity of your classifier, or in this case, our density estimation.
Question.
Yes.
I think these criteria, when we truly, on the real evaluation, when we want to evaluate how good our density estimator is,
Right.
for the bias part, we have no way to estimate that, right? We don't know the ground truth.
Yes. But you know what your performance is on, say, an independent test set, right? That's how we have usually been evaluating our estimators. So you can't decompose, you can't understand what the bias or the variance is, but you can understand how they trade off with each other by looking at the performance on a test set. Yeah. Good, go ahead.
I think part of what you're saying is that classification, for example, we have a ground truth in classification, but for density estimation, we rarely have a ground truth. So you don't know how you would evaluate that. Is that what you're asking?
Yeah.
So let me know if I'm not giving the right answer, but I think what people do is that we rarely want to evaluate the density of something for no other reason. We want to evaluate the density of something to then feed it into some other task, like classification, like clustering. So even if we can't evaluate directly how well did we do on density estimation, if we then use that density to do classification, then we can see that different density estimation methods lead to better or worse classification. So we're using a proxy task to see how good we did on our original task. Does that make sense?
Yeah. So that's part of the answer. Even if you are actually interested in density estimation, there are ways to do cross-validation for density estimation also, where you just look at your likelihood on a test set and predict using that. So there are ways to also do cross-validation to select the right size for density estimation task. But yeah, Ada's point is also good that most often you do it actually for some other task, and so you can still evaluate the accuracy that way. Yeah, thanks. Yep, that's a good point. All right, so far it seems like this is a very completely different approach we have taken, right, than what we had talked about earlier about estimating parametric distributions, right? So anybody remembers how we actually estimated distributions earlier? We didn't talk about specifically estimating distribution. We always talked about it in the context of classification or regression. But actually the methods we talked about we were plugging in estimates of distributions, right? And what were the two methods we were using mostly to do that, to estimate distributions or their parameters? Yeah, MLE and MAP, right? When we did maximum likelihood estimation or MAP, we were essentially just estimating distributions and then plugging it into a formula for classification, essentially. So those are two methods we used earlier, and you might say, well, those seem very different than what we did here, which was chunking up our data into bins and coming up with this relative frequency estimates. But turns out that there is a connection. You can actually think of histograms as maximum likelihood estimates under a specific model. And actually this might make a good problem for the homework or recitation. We won't go into the details here. But if you think, so I mean, what is histogram based off of? As we just said, like if the bins are so small that the value at each point can be effectively approximated by the average value in that bin, then we are good, right? So that's really what histograms are built off of. And in fact, you can see that if you choose your underlying model to be that the density is constant on each bin, so there is a particular value for each bin, which is not the case, but that if you buy into that model, that Pj is a parameter which is constant in each bin. And of course, if we choose these Pj's to be, say, probabilities of each bin, then the total density has to integrate to 1. So we might require that all of these Pj's, which are the density estimates, sum to 1 over delta. Or another way to think of it is delta times Pj is what your density is. And so you would require that to sum to 1. Right? So your point has to fall in one of those bins. Right? And then you looked at what's the probability of the data, what's the likelihood of the data being generated according to this set of parameters, which are just one value for each bin, and you look at the maximum likelihood under this model, then you exactly end up with the histogram density estimate. Okay, so that's a good thing to try on your own, or maybe you'll cover it in the recitation or the homework. But you can argue that under this particular model, if you do maximum likelihood estimation, you get the histogram estimator back. So that's why you can think of these values in each bins as the parameters of your model. Okay. All right. So let me mention one other thing that you might say, well, in practice, if we just count the relative number of points falling in each bin and output that as our estimate, it's going to be very blocky, which is true. So here there are a bunch of points sampled, again 1D points, and you can see there are more points here, fewer here, maybe some more number over here, and so on. And this is the histogram density estimate you get, and it is clearly very blocky, so maybe not such a good approximation to whatever might have generated these data points. So there are slight modifications that tend to work well in practice, and actually there is also theory behind them, where the idea is, well, one simple idea is let's not use fixed bins, let's not partition our feature space into disjoint bins, but let's do a moving window. So we fix a bin width, but then we output the average as the density at the middle of this bin, and then we can move the bin a little bit and output another average and keep on doing that, right? So in terms of formula, if you see, all I've done is here in the histogram estimate, so we are again dividing by 1 over the bin width, which is the volume, to convert the probability into a density estimate. But the probability is just how many points were there divided by n. And here, instead of chunking my space into these fixed bins, I'm defining a bin around the point at which I want to do the prediction. So if x is the point for which I want to estimate the density, I'll put a bin around x. And if now I want to predict the density at another point, I'll move my bin to be again centered at x. Right? And I'll keep on doing that. So this is still counting how many points fall in a bin, but this is not a pre-specified bin, it's a bin centered at the point at which I want to do the density estimate. Oops. All right. So if we do that, you can see that we get a much sort of smoother approximation to our density. And more generally, we can actually throw in this idea that we can replace, what I did here was we just defined something which was counting how many points lie in a small bin around our test point. I can replace this with any function, which is also called a kernel. And this kernel is slightly different than the kernels we've studied so far, but it's also referred to as kernel. So this is essentially a function which could be just saying count how many points lie in that bin, or it could be a weighted average of points around that test point x. Okay, so think of these as just weights based off of how far is your training point xj from the test point x. All right. So we'll talk about this. I think I should end here. It's we're over time. But this is what is known as kernel density estimate, where you can take this idea of how many points lie around test point to and make it into a kernel by saying weighted average. Yes.
How do you optimally pick the data with the kernel?
Right. So we will talk about that. We've already seen that affects the bias variance trade-off, and you can do that. As I said, there are cross validation methods for density estimation that you can use to pick that bin width appropriately. And there is theory that tells you how it should scale with the number of data points. Okay. Yeah. So we'll talk about this next class or on Monday, not next class.